Okay. Before we talked about legged systems, I want to introduce what are known as hybrid systems. So hybrid systems are systems where the the motion of the system has different modes. So for example, if you think about a bouncing ball, that has two phases. One is the phase when the ball is in the air, and it's described by equations of motion which we've derived in the past. And then there's this phase where the ball hits the ground. So that's basically described by empirical relation known as the coefficient of restitution. And then once the ball bounces back, it's back into the falling under gravity phase. So that's a hybrid system. So systems with different modes are hybrid systems. So example would be ball bouncing on the floor. Okay. Other systems are, well, legged systems are hybrid systems. So what happens is when you're walking, your legs are, one of your leg is freely swinging in the air, but then that leg hits the ground, makes contact with the ground, and then the other leg is released and it again swings. So that's again a hybrid system. Legged systems such as bipeds. Bipeds are a system with two legs, quadrupeds are a system with four legs, and so on. So to motivate this and to make it easier, I would first start with a bouncing ball, and we'll see how to simulate the system, because that's the critical part here, not really the equations of motion. And once we have developed the ideas for a bouncing ball, we'll then take that to a legged system and then analyze that system. So first example is bouncing ball. So what is this? Well, it's basically if you throw a ball in the air, then it'll fall down. At some point of time, it'll hit the ground, and then it'll bounce up to a certain height, then fall down, and keep doing that till it eventually comes to rest. So bounce one, bounce two, and so on till it comes to rest. Now I'm just showing it moving slightly to the right. It's really falling in the same place, but I can't quite show it on the same line. So I'm just drawing it at different points, but you get the idea. It's basically to bounce up and down till it eventually dies out. Okay. So the question here is, how do we analyze or simulate such a system? Okay, so first thing I like to do is to think of the different phases or the different modes which the system exists in. So there's a mode where system is in the air. So analysis. So this is free fall. Okay. At some point of time, the ball is going to be right here, but it's moving downwards. So this is just before bounce. And then once it hits the ground, it will rebound. So this is V, showing the arrows denotes the direction of the velocity, and just after bounce. Okay. Okay, so that's what happens to the ball, but let's try to write an equation which describes the motion of this ball. So free fall. Okay. Now, once it falls freely, you need to have a system where you can detect the ground. So normally the ground is, well, if you think of y describes the height, then y equals 0 is the location of the ground, right? But it could be anything else. It could be dropped on a table, which means that y will not be equal to 0. Then there is the bounce. Okay. Then once it bounces off, which is basically these two phases, so free fall and then bounce. After that, it will again fall under gravity. So it will be free fall. And then again, there'll be a bounce. Sorry, this should be detect ground. Bounce. And so on. So you can see that it's basically cycling between free fall, bounce, free fall, bounce. And it just, to simulate this system in MATLAB using your own equations, it's more meaningful if you think of the repeating unit, simulate that repeating unit as one single phase, which is, let's say, one bounce. And then once you have one bounce, then you can just call that function which does one bounce n times to do n bounces. So what we'll do is we'll identify what is that building block which we can use, which we can call or simulate in as a function, so that we can call it, keep calling it. So this is one complete bounce, right? Which involves falling under gravity, detecting the ground, and bouncing back off. Okay, so if you can simulate this unit, then you can just call it in MATLAB multiple times to simulate more bounces. So this is the repeating unit. Okay, so that will be our goal. Our goal will be to simulate this repeating unit. Okay, now once we have identified the repeating repeating unit, we need to describe the motion of the system within that repeating unit. So that's free fall, and the second one is bounce. So one is free fall, and second is bounce. So now I'm going to write the equations for both those two parts constituting that repeating unit. Okay, let's go on. So first, let's do it for free fall. Here the ball is falling under gravity. If you like, there's a mass m. And in this case, since the motion is only along the y-axis, I don't really need to write the equation for the x-axis. So you can use Newton's laws, you can use Euler-Lagrange equation. The equation of motion in this case is simply the acceleration is minus g, where g is gravity. Okay, there is no drag force here. The second is the bounce. Now this one is slightly different. I need to draw two diagrams here. One of the diagram is going to be just as the ball is moving downwards with the velocity v, and then there is the phase where it bounces off v. Now to make it, instead of calling it v and v, what notation I'll be using is I'll call the velocity before bounce as v negative and v positive, or you can write it as v dot, oh sorry, y dot negative and y dot positive. So y dot negative is velocity before bounce, and y dot positive is velocity after bounce. So for this one, for this particular phase, the equations are, well, they're empirical equations called by Newton's law of restitution. law of restitution, okay, which is basically an empirical law. You need to do an experiment basically to figure out this law. There's a coefficient of restitution which describes the velocity before bounce to the velocity after bounce. So here it is E equals, so that's the coefficient of restitution. And that's simply the velocity after bounce, so y dot positive divided by y dot negative. So our day-to-day experiences tell us that if the ball is hitting with a velocity y dot positive, then the velocity after bouncing off will always be less than the velocity before bounce, right? And then I forgot the sign. Sorry about that. So it's actually minus e. And that's because the velocity is going to be redirected. That's why we have the negative sign. So we know that from experience that E is always less than 1. Because if you drop a ball, it will not bounce back higher than where you dropped it from. Okay. If E is 0, which means that y dot positive is 0, that means the velocity after bounce is 0, which means that the ball has actually stuck to the ground. So that's a purely plastic collision. So y dot equals 0 or E equals 0 implies y dot positive is equal to 0. This is a plastic collision. If E equals 1, y dot positive is equal to minus y dot negative, which is just saying that it's a purely elastic collision. Okay. Most times E is between 0 and 1. We never really see 1 because it's really hard to have a purely elastic collision. Okay. Okay, E greater than 1 means that the velocity after collision is greater than the velocity before, which never really happens unless there is some kind of actuator which is powering the system to jump higher than where it started from. So what I've written down are two equations, one for the bounce. Okay, I can maybe rewrite this as y dot positive equals minus c y dot negative. So that way it's easier to write it in Matlab. So E is given to you, velocity before bounce is known. We can find the velocity after bounce from that formula. And the second equation which we need is this equation. So let's call this 1 and let's call this 2. And so we need both these equations in order to simulate the system. Okay. So before we go to simulations and I show you the code, a few things I want to mention about simulating the system. Simulate in Matlab. Okay, so the first thing we need to do is we need to write a function called one bounce, okay, which basically does free fall, detect ground, and then bounce. So we need to basically write this function. That's my goal. The second thing which is kind of interesting is when we do free fall, which is described by y double dot equals minus g. What we're doing is we are using an integrator. It could be ODE4, ODE45, and whatever you like. When we normally solve, when we use ODE4 or ODE45, we are integrating the equations for a given time. So 5 seconds, 4 seconds, 3 seconds. And some point we stop the integration, and that stopping is really time based. But here we actually need to stop the integration when the ball hits the ground, which is saying that, so this is time based. We need to stop the integration when y equals 0, right? That is when we detect ground. So we need a mechanism inside the integrator to tell us to stop the integration when this occurs. So time is unknown. In other words, time is unknown. Okay, so we need to find the time such that y equals 0. So if you recollect your project where you were doing bouncing off the ball against a wall, that's precisely the same problem, which is you were just integrating, in that case, Euler's method. And then whenever you see that the ball reaches one of the walls, I think it was x equals 10 or y equals, the up wall was y equals 100 or something like that, you basically reverse the velocity of the ball based on the same condition which I showed you, restitution. Okay, so that was using Euler's method, which is not very accurate. And so I'll show you a much accurate way of doing this using ODE45. Okay, so we'll use ODE45 to do this. How will we do it is inside ODE45, there is something called options. So it's one of the argument. This is where you set the ODE set. So you need to set some options. So one of the options we usually set is abstol, which is the absolute tolerance. Another option is actually called event. Okay, and this is basically is where you will set the detect ground. There's a very precise way of setting detect ground such that when the detect ground function is comes out to be true, when y equals 0, the integration will actually stop. Okay, and I'll show you how to do that. So once we have these two ingredients in the free fall and bounce, then we just have to integrate these equations for 5 bounces, 6 bounces, or we can just integrate it for 10 seconds, 5 seconds. But it's important to find the time, stop the integration when we detect ground each time we go for a bounce. So I'll show you the Matlab code, which will do it. So this is basically a function handle. It basically is, you can see that we have a function here because it has a bracket. And in that bracket, we are passing one of the arguments to be detect ground. And so when you want to pass a function within a function, you want to use at sign. Okay, you can also search. Let's see, just give me anything useful. No. I think the way to search this is to say function, Matlab function handle. So you can read more about function handles here, creating function handle, okay, and understand it. So let me just send this through the chat window. Okay, so here's the code which I wrote. Let me first run the simulation. Okay, so that's the bounce. I also have some figures. Figure 1. Okay, so that was basically plotting the position, and this one is not showing me the, it should have shown me the velocity, but never mind. Let's start this in a bit again. Okay, so as I said, the main crux of this thing is to write this function called onBounce, which basically does two things. One is integrate the equations, which is here ODE for phi, and then applies the restitution condition, which is saying that the velocity after bounce is equal to minus e times velocity before bounce. And once I have this system set up to do a single bounce, I can just keep calling it within ball main. And so you can see all I'm doing here is for t going from 0 all the way to my end time, which is 5, 10 seconds, whatever you want, I need to call onBounce. Okay, so within onBounce, we can see there's options, and this is where I pass, I set the options for the integrator. The key option here is the detect ground, which is a function telling MATLAB till what time you need to do the integration. So normally I'm integrating from 0 to 5 seconds, but between that time, the ball actually hits the ground. So let's see what detect ground does. That's an additional function which I've defined here. So the function which does this, called events, has a very specific way in which you need to define it. It needs to have this g-stop, which is telling me when you want to detect the ground. So in this case, ball.ground is basically set to 0. So ball.ground is 0. So y minus ball ground should be 0. And then the direction is telling me which direction the ball, I need to detect the ground. So there are two ways in which that y equals 0 can be detected. One is when the ball is falling from above the ground onto the ground. So in that case, the velocity is basically negative. And the other way in which this can hit is that the velocity can be positive, in which case it's sort of hitting the ceiling. Okay, I don't want to detect the ground when it's going upward. I want to detect when it's going downwards. That's why I put a -1. And then if you want to stop the integration, then you put 1. Okay, so there was one question. Does the callback function have all arguments same as the main function, or can we send a different value? Example, ground might change based on time. If you want to change the ground height, you can actually do it by sending a different ball.ground. In fact, I made it a function. So you could just call it, you could change it after 5 bounces. You can decide it could be y equals 5. I can do it if you want. In just a bit, I'll do it. Okay, and then let's see. And then there is this file, which is the right-hand side for the falling under gravity, which is basically equations of motion, which is saying that the acceleration is minus g. Okay, so run this again. And you need to adjust the speed of the animation so it looks realistic. So what works for my computer may not work for your computer, and you might have to change the delay. Okay, if you want to change the ground, let's say we want to change the ground from 0 to 1 meter. Assuming I'm throwing the ball from a different, okay, I'm throwing the ball from 0. Let me just throw it from ball.ground. So now you'll see that the ball starts at 1 meter from the ground and then jumps. So you'll see that the ground is still at 0. So you don't quite see the ground because it's buried at 0, but you can see it's bouncing approximately at 1. So when it's 1, it's actually, the 1 here is actually the center of the ball. I did not quite adjust the height so that it's actually I did not put the radius of the ball in my animations, but you could definitely put the radius. In this case, the ground is going to be, you take the radius and you need to move the ground by that much in order to make it look like it's falling from the ground. Okay, let's put this back to 0. Okay, any questions on this?